Section 4.4 is on simplifying algebraic expressions involving radicals. So we're first going to start off with three different radical expressions and going to evaluate each of them for a set of values from -2 up to 4 for the x and see if we can come up with some generalizations. So the first one here, we've got the square root of x, and if we plug in -2 for x, we end up with the square root of -2, which is not defined. It's not a real number. If we plug in x equals -1, we get the square root of -1, which is again undefined because you can't find the square root of a negative, and that's not a real number. If we plug in 0, it's okay because the square root of 0 is 0. If we plug in 1, we can work it out. The square root of 1 is 1. If we plug in 3, the square root of 3 is not a nice rational number, but it is defined. It's around 1.7. And the square root of 4 is 2. So if we look at the values for x in this particular expression, it seems like only those values that were bigger than or equal to 0 were values for which this expression is defined. So x bigger than or equal to 0 seems to work here. In the second expression, if we plug in -2, we get -2 minus 1, which is the square root of -3, which is not real. And if the second one we plug in -1, we get -1 minus 1, and that gives you the square root of -2, which is again not real. And if you plug in 0, you get 0 take away 1, which is the square root of -1, which is still not a real number. You can't find the square root of a negative number in real numbers. Then if we put in 1, we get 1 minus 0. That gives us the square root of 0, which is 0. And if we plug in 3, we get 3 minus 1, which is the square root of 2, which is a defined value in the set of real numbers. I think it's approximately 1.4 around there. And the square root of 4 take away 1 is the square root of 3, which is also defined in the set of real numbers. So if we look at the values that for this expression where it was defined, it seems to be once we got to x equals 1, everything bigger than 1 seemed to work, but the numbers less than 1 did not. So we had to define where this was describe where this was defined. It would be x bigger than or equal to 1 would allow this expression to be defined. So now if we look at the last expression and plug in the different values of x, the first one is -2, so this would be the square root of 3 minus a -2, which becomes the square root of 3 plus 2, which becomes the square root of 5, which is a defined value. If we plug in -1, we get 3 minus a -1, which is the square root of 3 plus 1, which is the square root of 4, which is again defined, and that can be simplified to 2. If we plug in 0, we get 3 minus 0, which is the square root of 3, which is also a defined value. And if we plug in 1, we get 3 minus 1, which is the square root of 2, which is also a defined value. And if we plug in 3, we get 3 minus 3, which is the square root of 0, which is 0, so that's defined. But if we plug in 4, we get 3 minus 4, which is the square root of -1, which is not defined. This is not defined, the set of real numbers. So if we kind of examine those values, it seems like anything that's less than 3, in this case, less than or equal to 3 works, and anything that's bigger than 3 doesn't work. So we had to define this expression. We would say that x would have to be less than or equal to 3 in order for that expression to be defined. So basically, if you look at generally all those expressions, when they were defined and when they weren't, it just basically seems that the only values of x that make the expressions work are the values of x that when you plug them back into the expression give you a positive value under the square root sign. If they give you a negative value under the square root sign, they're undefined. So you would basically need, if you want to make a generalization, you would need the expression under the square root sign. To be basically a positive or equal to 0, and then it works. So if we look at what we call restrictions now, restrictions basically are the values of the variable in expression that ensure the expression is undefined. The square root of a negative number cannot be evaluated. This means the expression under the root sign must be greater than or equal to 0. And to find restrictions for a radical of the form square root of an expression, we need to solve the expression greater than or equal to 0. So basically, if we're looking for the restrictions, we just take what's underneath the root sign and solve it greater than or equal to 0. So for the first example, we're asked to state the restrictions for the variable x in each of the following. So for the first one here, the expression under the root sign is x plus 3. So we would need x plus 3 to be greater than or equal to 0, which means x would have to be greater than or equal to negative 3 if we solve that inequality for x. The second one, we need the expression under the root sign x minus 6 to be greater than or equal to 0 in order for that to be defined, which means x has to be greater than or equal to 6. The next one, the expression is 4x plus 2 under the root sign, square root sign, so that has to be greater than or equal to 0. So if you solve that for x, you get 4x greater than or equal to negative 2, and then if you divide both sides by 4, you will get x greater than or equal to negative a half. So that means if you pick x as bigger than or equal to negative a half, that expression should be 0 or positive, and then you will be able to find it. So again, same ideas. This one here, the 6x minus 2, is what's under the root sign. So that has to be greater than or equal to 0 in order for this square root to be defined. So if you solve this for x, you have to basically add 2 to both sides, give you 6x is greater than or equal to 2, and then divide out the 6 to get x is bigger than or equal to 1/3. The next expression, you need 2 minus x to be greater than or equal to 0, which means that if you want to get the x by itself, you need to take that positive 2 and subtract 2 from both sides, so that's going to give you negative x greater than or equal to negative 2, and then in order to get x by itself, you have to divide both sides by negative 1, and when you divide both sides by negative in an inequality, you have to change the direction of the inequality sign. So that would give you x is actually has to be less than or equal to positive 2. And you can check to assure that that's right by picking values less than 2. If you plug them back in here, 2 minus less than or equal to, if you say for example x is 2, 2 minus 2 is 0, you can find the square root of 0. Pick another number that's less than 2, like 1. 2 minus 1 is 1, which you can find the square root of that. But if you pick something that was bigger than 2, not less than or equal to 2, if you pick something that was bigger than 2, like 3, you'd get 2 minus 3, which is a negative. So this does appear to be right. The next, last one there in this expression, in this example, you need 12 minus 3x is the expression under the root sign, so you need that to be greater than or equal to 0 in order to find the square root of it. So that means negative 3x has to be greater than or equal to negative 12, and then if you divide, well, actually I'm going to have to go down to the next line, because if you divide both sides by negative, you have to remember to switch the direction of the inequality sign. So you end up with x is less than or equal to positive 4. And you can again always go back and check values less than 4 into this expression for x, plug them in and see if you are getting defined values for the square root. So another thing you have to consider is if a radical is in a denominator and there's an expression involving a variable in that underneath that radical sign, then you also must consider that you can't have a denominator of 0. So that means the expression on the radical symbol will not be defined for greater than or equal to 0, just for greater than 0, because you don't want the expression equal to 0, or else you'll have 0 in the denominator. So the first one here, you would need in this case x plus 7 to be just greater than 0, because if it's equal to 0 you'll have a number that's undefined. So x would have to be greater than negative 7, and the question B there, you'd need the expression under the root sign 3x minus 4, because it's a radical that's in the denominator. You don't want that to have a value of 0, so you need that to be greater than 0. So 3x would have to be greater than 4, and then you divide both sides by 3. So that would mean that x would have to be greater than 4 over 3. So far we've looked at linear expressions under the radical sign. Now we're going to look at some powers of x and see what, or if we need restrictions for those powers of x when they're involved in radicals. So the first one we're looking at is the square root of x squared. X squared is always equal to 0 or a positive, because when you square 0 you get 0, and when you square a negative times a negative will give you a positive result, and when you square a positive times a positive will always have a positive result. So therefore there should not be any necessary restrictions if you have the square root of x squared, because everything will be a value that you can take the square root of. It'll either be 0 or it'll be a positive value which you can find the square root. Now when you get to x cubed under the root sign though, if x is positive, that means you've got a positive number cubed, which is going to be a positive times a positive times a positive, which is going to stay as a positive. But if x is negative in value, that means you've got a negative value cubed, which is going to end up being a negative. And if you try to take the square root of it, then you would get an undefined value. So therefore, you would need to have x greater than or equal to 0 in order to be able to find the square root if x is cubed under the radical sign, under the square root sign. X to the 4 would kind of follow along the same property of x squared, because if you raise a value to a power that's even, if the exponent is even, then it's going to be always positive or 0 if x is 0. Because a negative multiplied by itself an even number of times will always be a positive result. And the same thing with a positive multiplied by itself an even number of times or any number of times would always be positive. So therefore this one would have no restrictions. But now if we go back to another odd power of x, we get to the same kind of result as we did up here. If x is positive, it's going to be a positive to the power of 5, which is still going to be positive. But if x is negative, you're going to have a negative multiplied by itself an odd number of times. So therefore you would need x to be greater than or equal to 0, because a negative multiplied by itself an odd number of times is going to be negative, and you won't be able to find the square root of it. So if we look at a summary of that, the restrictions for radicals of the type x to the power of n would be what restrictions exist when there is an even exponent. There would be no restriction. And if it was an odd exponent, you would need x to be greater than or equal to 0 in order to define the square root. So now we're going to have a look at some radicals which with index of 2. We're going to look at square roots that contain a variable radicand. And the first question asks us to look at see if we can find the error in the statement. The square root of x squared equals x And the error in that statement is better understood when you think about certain values of x. For example, if x was equal to 2, that would imply that if the statement is true, that 2 squared, which is equal to the square root of 4, which is equal to 2, x in this case is 2, and the square root of x squared is in fact x. X is 2, and the answer is 2. When we take the square root of x squared, we do get x back, because the square root of 2 squared is 2. However, if we consider x equals negative 3, then we're taking the square root of negative 3 all squared, which is actually the square root of 9. And when we use the square root symbol, if you remember from earlier in the chapter, this square root symbol means the positive answer or the principal square root, which means the answer is 3. So in this case, x was negative 3, but the square root of x squared was not actually equal to x. It was the opposite of what was being squared under the radical sign. So the error in this statement is that the square root of x squared can be x if x is positive, but it's the opposite of x if x is negative. Okay, so if we consider using the square root symbol with x squared, we know that that means that we have to have the principal square root, which is always positive. So in order to ensure that the square root of x squared is a positive answer, because as we saw in this example here, x could in fact be a negative squared, and we don't want the answer to be a negative, we would have to take what's called the absolute value of x. And the absolute value of x is the distance that a number is from 0 on a number line. So the absolute value of x is exactly the same as x if x is a positive number, or bigger than or equal to 0. And it's the opposite of x if x is less than 0. So that's why the the absolute value of negative 5, these symbols here, these lines around x, mean absolute value. You put two straight lines based on either side of x, that means the absolute value of x. If we're finding the absolute value of negative 5, right here, that distance from negative 5, that negative 5 is from the number line, 0 on the number line, is actually positive 5 units, because distance is always measured as positive. So therefore, anything that's a positive number, absolute value of x would be exactly the same, but if it's a negative number, absolute value of x would be the opposite of it. However, that can get kind of tricky when you're doing these simplifying expressions when we're doing in this chapter. So for the purposes of this course, we are going to assume that every time that we have a square root using the square root symbol, and we have a radicand that contains a variable, we'll be assuming that the x that we're starting with is the principal square root of x squared, and we won't, we'll just basically, in other words, assume that we're only dealing with positive x's, so that when we write the square root of x squared, we won't have to use the absolute value. When we take the square root of x squared, we're going to assume all our x's are positive, and the square root of x squared will be x, just to make it a little bit easier in our workings. So, keeping that in mind, how would you define higher powers of x? So the square root of x squared is x, because x times x will give you x squared. And the square root of x to the 4 should be x squared times, or just should be x squared, because x squared times x squared gives you x to the 4. And similarly, the square root of x to the 6 would be x cubed, because x cubed times x cubed, using our rules of exponents, would give you x to the 6. If you remember also, in grade 10 math, when we had the square root of x to the n, it was the same thing as x to the n to the half. The square root is the same as raising to the power of a half. So that's why when we had x's exponent of 2 here, the square root would basically half the exponent. So you end up with x to the, what's understood to be a 1. And if we take the square root of x to the 4, it's like taking half the exponent, which is 2. And the square root of x to the 6, take half the exponent, would be x cubed. Okay, and similarly for other higher powers of x that are even. So we'll do some examples now that have some odd powers of x, just to show you what happens when we get to those. So the first one here, example, is the square root of x cubed. So what we do, similar to what we did when we were dealing with numbers, we break it down into perfect square powers of x. So this would be x squared would be a perfect square factor of x cubed. And then we still have a one little left over x. And then the square root of x squared can come outside as an x. And we're left with just the square root of x inside, or under the radical sign. Similarly, we can break down the square root of x to the 17 as x to the 16 times x, because that's an even power which is basically a perfect square power of x. And x to the 16, if you take half, that would be x to the 8th would come out, and you just have the root x left underneath the radical sign. When we combine numbers with powers of x, we just basically do the same thing we did earlier in the chapter, but now we have some x's with it. So 8 breaks down as perfect square factor 4 times 2, and x cubed breaks down as x squared times x. So then the square root of 4 is a perfect square. 4 is a perfect square, so the square root of 4 comes out as a 2. And the square root of x squared is a perfect square, so that comes out as x to the 1. And then all we have left underneath is 2x. So 2x, root 2x would be our answer. This one here would be 4 times 18 has a perfect square factor of 9, so 9 times 2 is 18. And x to the 5 would be x to the 4 times x. So then this would be a perfect square, and this would be a perfect square. So 4 times the square root of 9 would come out as a 3. And the square root of x to the 4 would come out as x to the half of 4, which is 2. And then we'd be left with just the 2 and the other x left inside. Okay, and the next one here would be negative 7y squared. And the 8 we could break down because it has a perfect square factor of 4. So 4 times 2 is 8, and y to the 5 would break down as y to the 4 times y, which would be negative 7y squared. Perfect square of 4 would come out. Square root of 4 would come out as a 2, and perfect square of y to the 4 will come outside as a y squared. And then we'd just have the 2y left inside, or underneath the radical sign. Okay, so that's the end of that little part there. So these are some questions you can try related to what we just did so that you can get some practice.